Okay, I haven't yet given any hints for part 3 of the homework. And let me make this bigger so you can see what's going on. Okay, zoom in a little bit. Okay, here we go. Now, part 3 says Hessenberg form. Hessenberg form writes A as QR, where Q is orthogonal, and R is upper triangular. Okay. So let's see what we have here. And Q may not actually be square. Q may be rectangular. Right. So let's look at this case here, where we have QK transpose AQK equals HK. Now HK and A are almost similar, so there's a relationship between their eigenvalues. Okay, so let's see if we can explore the relationship between their eigenvalues. Now, why do I say almost similar? Because, as I said, QK may not be square. So the dimension of A and the dimension of HK may be different. In fact, if QK has K columns, then you can verify that HK is K by K. So QK could be a N by K matrix. And A would be N by N, H would be K by K. All right, so we've shown in 1D above that if the rank of A is K, then AX blah blah blah, these K vectors are linearly independent as long as the coefficients Cj are non-zero and the non-zero eigenvalues are distinct. Okay, so we're using this hypothesis. Cj are non-zero, non-zero eigenvalues are distinct. Show that these span the column space of A. Show also that Q1 through Qk produced by the Arnoldi process also span the column space of A if we make the choice B equals AX. Okay, so let's see. So what I'm saying here is use a dimension argument. Okay, we want to show that these K vectors span a certain space. And in general, if you have n, well, let me just use a general letter here. If I can take any letter here, m linearly independent vectors in an m-dimensional subspace always span the subspace. They always span the subspace. Okay. All right. So I emphasize that these vectors have to be in the subspace. So here you have k vectors in a subspace, the column space. So that should give you some idea of what you need to prove. You need to show that these are linearly independent vectors in the subspace, and you have to show that there's enough of them. All right. Then for the Q's, well, you have to think about how you obtain the Q's. You can actually do a similar argument for the Q's. So I'll just say similar argument for the Q's. You certainly will need to show that these Q's are in the column space. And then you'll have to show something about linear independence and how many there are. All right? All right, so that's this one here. Part B. All right, now, we're in a k-dimensional subspace. We have k vectors, and the rank, and A is an n by n matrix. Okay, so the size of A is bigger than the rank. So what we're going to do is we're going to take our k orthogonal vectors in QK, and then we're going to fill them out. We're going to find an orthogonal basis for the null space of A. I'll just tell you that the null space, every vector in the null space is orthogonal to any vector in the column space. We've talked about that before. So here we have an orthogonal basis of the null space. Here we have an orthogonal basis of the column space. We want to show that if we put them together, we have an orthogonal basis of all of Rn. Now, so you're going to use a similar argument, but you have to show something here. You have to show that these are linearly independent. Okay, and you can show that by showing you can follow this hint here. So they're all linear independent. And you can show this. So you can say one way is to show they are all orthogonal. Okay. If they're all orthogonal, and of course then non-zero, okay, we have talked about how orthogonal vectors are always linearly independent. Okay. So you can use the dimension argument again. Okay. So we're trying to reduce things. Instead of taking Q transpose AQ, we're taking QK transpose AQK. So as I said, this may be a smaller matrix and more convenient to work with. So I'm going to show that these have the same non-zero eigenvalues. Okay, and so no, the qk is the first k columns of q. Okay, they have the same non-zero eigenvalues. Okay, here we're assuming that the rank of a is k. All right. Okay. All right. So qk is the first k eigenvalues. So let's see. So here's a hint that you could follow. Let v be an eigenvector of A with non-zero eigenvalue. Okay. You know that this eigenvector is in the column space of A. So you figure out why. You have to give a reason for that. If it's in the column space, you can write it as a linear combination of the q of the q's up here, of these q's up here, because we showed that these q's form a basis of the column space. Okay. So I'll write this linear combination as qk. Is that a q? It is a q. Qk times a column vector c. Okay. Okay, so I want you to rewrite this linear combination as qk times a column vector. Then show that c is an eigenvector of this matrix here. Yeah, you can do that, right? If you just write down this matrix times c and do some algebraic manipulations, you can show that c is in fact an eigenvector of this matrix here. Now this, I'm being sloppy here. qk just means q sub k. I didn't want to take the time to do all the fancy stuff. Okay. So on the other hand, take an so this should this will show that every eigenvalue of A, every non-zero eigenvalue of A is an eigenvalue of this other guy. But we're not done, right? You can show that, but you also need to show the other way. You know to show that every eigenvalue of this is also an eigenvalue of this. Okay, so you can do that basically the backwards argument. Take an eigenvector of this matrix, and then you can show that qkw is an eigenvector of A with the same eigenvalue. Okay, so you can run the argument both ways. All right. Now, last part. Let's get into the Python now. And nobody was able to complete this, and let me get you jump started. And what I'm going to do is, as I mentioned, you can do this step by step, and I recommend you try that. I'll actually work out the first few steps for you on this one. So here's our matrix. And I'm going to pull this over to my other window so I can copy it into my Jupyter. Okay, so I'm going to go into Jupyter, and my Jupyter should be somewhere. Let me pull up my Jupyter. Actually, it's in the same place, right here. Okay, we'll take it here. Here's my Jupyter. I want a new file. We're going to start from scratch. Now, I think I gave you an outline file, but I'll just start from scratch. Now, you're going to need NumPy. So I'm going to do from NumPy import star. Okay. That means all of my or I don't remember if I did it that way or if I did it the other way. Maybe I should do it the other way. Import NumPy as not numt, NumPy as NP. Okay, we'll do it that way. Okay, so we're going to need NumPy, and let's see, we're going to need our array, and our array was, it's covering up. Let me move this here. Okay, so I'll just call this A. A equals, and the way you do an array is array, and then I'm going to do the array of rows. So this is 1, 2, 3, 4. Then it's 5, 6, 7, 8. And then this one was 9, 10, 11, 12. And then this one was 13, 14, 15, 16. Okay. All right. Now, it's good to know whether I've done this right. So I'm going to print A. Okay. Now, I can run this. Okay. Array is not defined. I forgot the NP. So let's put the NP in there. NP.array. Okay. So let's see what happens here. I'll run like this. And there we go. Looks good. Looks fine. Okay, good. Now I have another cell, and let's build on that. Now, let's look at what we have here. As I said, I'm not going to write a program. I'm just going to do this step by step using as a calculator. So first of all, it says Q1 equals B over absolute B. So some people ask me, what is B? Let's just take B to be anything. Okay, so we'll start with some b. Now that may cause a problem if we choose. We know that for some b's it may not work, but let's just go ahead and try some b. Okay. So here I'll make a comment here. I'm going to create the vector q1, and I'll just call it q1 like this. Okay. So here I'm going to take a b, and b is going to be an array, and let's just make it 1, 1, 1, 1. Okay. All right, then what we have to do is take q1 is b over the norm of b, if you saw that. Now if you look up, if you go to, I'll just show you how you do this. You just look up a vector norm in NumPy. And there it is, numpy.linalg.norm. Okay, you can look at the manual and you can see how it works. It looks pretty straightforward. Usually they give some examples at the bottom. And all they do is, here they have LA norm, but I think what I want, let's see. Well, they put the norm afterward. So you can do it that way. I'll actually do it the same way they do it. So if you do that, you can do what? Let me see how they imported this. Oh, if they import linalg as LA, that's why they do it. So I'm going to keep it as linalg. Okay, so I'm going to, instead of doing LA, I'll do linalg. Well, why don't I just go ahead and do this the same way they do it? That looks nice. So I'm going to import linalg as LA. So we can do it the same way. A number of ways you can do this. This is one way. All right, there's not a unique way of doing this. So I'm just going to say, I need to take q1, and as I said, q1 is b over the norm of b. So q1 is equal to b divided by la dot norm of b. And then let's just make sure q1 is correct, so I'll print q1. It's always good to print what you're doing step by step to see if everything's working. Now I can type run here and see what happens. All right, let's see. No module named linalg. So this must be np.linalg. Let's see if that works, because this is from NumPy. Okay, let's try numpy.linalg. Okay, well, this trial and error sort of thing. There we go. So I got it that time. I got it that time. All right. So now we've got this vector q1, and you can verify that the norm of this q1 is equal to 1. Actually, we can do that down here just to verify la.norm of q1, and I'll print that. Whoops, sorry. Don't know why that came up. If I print this, then let's see what happens. Actually, if you press Control Enter, it will run this. All right, so you can see the norm was 1. Okay. Now I don't need this print anymore, so I'm just going to leave this off. All right. So I created my vector q1. Let's see what the next step is. Next step is what? Okay. Okay. All right. So what this is saying is I have to create my v. Why did it do that? I have to create a v. V equals aqk. And notice that k is going to go from k is going to go from 1 to the last value. Okay, so in this case, I'm going to go up to 4, right? Because I'm going to want 4 vectors. So I'm going to start with k equals 1. Okay, so that's what my so I'm going to begin with k equal 1. Okay, and now let's see what we have here. We have v equals aqk. So I'm just going to say v equals a. Now remember, matrix multiplication is at. And that was supposed to be q1, right? All right, let's make sure I did it right. Control Enter, and it looks okay. All right, so I don't think I need that print statement anymore. All right, so what's my next step? Next step from j is 1 to k. Now in this case, k is 1, so we're just going to do j equals 1. So I'll put a comma here. Does j equals 1 is my first step. All right. So when it says j equals 1 to k, I'm going to do these 2 steps, however many times that will be necessary. This time I only have j equals 1 because j only goes from 1 to k, and I'm starting with k equal to 1. All right, so let's be careful about our indices. At this point, j equals 1, k equals 1. So this is going to be h11. So let's go ahead and do h11. Okay, now you can also figure out there's a transpose there's a transpose function. We can find out what that is. We can look for so numpy transpose. Okay, and let's see what we have here. Actually, it's just numpy.transpose. Okay, so let's look at that. So we can do numpy np.transpose, and that's going to be, let's see what it was. It was qj, and my j is 1, so this is just q1. And then this is matrix multiplication, so it's at v. Okay, and let's print out h11 to make sure that it's okay. Okay, okay, so let's see what happens. And we get a number, 34. And you can go ahead and verify that, in fact, that's correct. Okay, since it came out correctly, I don't think I need to print it anymore. Okay, so then we can go v is v minus, so the next step is v equals v minus h11 times q1. Okay, so v equals v minus h11. Now this is not matrix multiplication because h11 is a number. So this times this. And let's print v. Okay, and here we get a vector. I don't know if it's right, but it looks reasonable. You could check it by hand. Now, I only go through the loop one time because j only goes up to k. Okay, so I'm done with a loop and I go here. Now what is k? K is equal to 1, so this is h21. So I have h21 is equal to, and then la.norm of v. Okay, and let's go ahead and print h21. And I don't think I need, well, I can print both of them. Let's see, so this is my v, and then this is my h21. Okay, so I've got a h21 here. And I need to divide, let's see, there's one more step here, I believe. All right, so this gives me q2. q2 is v over this number. So my q2, so I'm going to erase this because I don't think I need it anymore. q2 is equal to v over h21. Now print q2 and run it again. And we get something here. And let's verify that q1 and q2 are orthogonal, because they should be orthogonal. So let's print np.transpose, that's right, of q1 at q2. And see, what we should get is 0. Okay, and we do. We get 0 down here, we're good. Very nice. All right, so I'm done with this. I don't think I need these print statements anymore. So I'm just going to take these out. Okay, let's go to my next step. My next step is going to be k equals 2. Whoops, let me go ahead and run. Okay, all right, so my next step is going to be k equals 2. Okay, so really this is not so bad, right? It's really not so bad. So here I have v equals aq2, right? So I'm going to use the same letter for v. In fact, I can probably copy and paste this and then make some changes. So I'm going to copy this and I'll paste it here. And now this is q2. All right. Now I am still going to go through j equals 1, but I'm also going to have a j equals 2. All right, but we'll get there. So we can do j equals 1 again. So here's j equals 1 and k equals 2. So just to distinguish between this one, this is j equals 1, k equals 1. Okay. This is j equals 1, k equals 2. Now be careful about the indices here. What are the indices on this h? Well, it's hjk, hjk. J is 1, k is 2. So I have 1, 2 here. Then what's on the other side? jk is qj transpose v. J is 1, k is 2. So I still have the q1 and the v. Now this v is not the same as this v. It's changed. Okay? All right. So now this v here, this next one here is going to be v minus hjk qj. Now my hjk is 1, 2, and my qj is 1. So this is going to be 1, 2 times q1. Again, this is a times because it's a scalar number. All right. So I've gone here, but now I have to continue through the loop. Okay? So then I need to take j equal 2. Okay. All right. So I have to do the same 2 steps, which I'm going to copy, or same 3 steps actually. Oh, I'm sorry. I put this in the wrong place. This should go here before this step. Okay. I'm going to do these. I'm going to do these same 2 steps again, but a little bit different. So I'm going to copy this. It's 2 steps, but the indices have to change. All right. So when j equals 2, k equals 2, you can check that this should be kh22, and this should be q2. Okay. And then this is going to be h22 and q2. Okay. All right, and that's going to finish the loop, and then here's going to be normalize and obtain q3. Okay. All right, so we've got this. Now this is going to be this is going to actually be h32 if you check the indices. And this is going to be my q3. Okay. Now, if this is all right, then my q3 should be orthogonal to q1 and q2. Okay? So q3 should be orthogonal to q1 and q2. All right, let's see if that's true. All right, I can check it the same way. So I'll do print, and then we'll do np.transpose of q1 at q3. First of all, I should print q3 just to make sure that I've got something good here. Okay. Well, let me print v also. I'll print v. I'll print q3. Well, let's not get too many print statements. Let's just print v first and see if we're on the right track. Okay. So I'm going to run this and see what all right, now look at something here. Look at this. Look at this. This v is basically 0. Okay? This v is basically 0. So what does that mean? That means I'm finished. That means that, in fact, my matrix is not a full rank. Okay? So the result shows that A has only 2 linear independent eigenvectors. Well, it may be that I started with a bad value. Let's start with a different value. I'm going to go back up here and start with a different x. Maybe the 1, 1, 1, 1 is not so good. Maybe I start with b something else. So I don't know, let's try something that's really fancy. We'll do 113 minus 2, 7. All right, that should certainly be okay because it's so random. So let's run through all of these again. Run. That's the same. Now q1 is going to change because I have a different starting vector. Run again. Okay, I got a different starting vector. This is blue, so it means I can run this one. Let me run it again. Well, before I run, let me check and make sure that this number is, let's do a print v, make sure we're not getting 0. And then we can also print, just make sure that q2 is orthogonal to q1. So I'm going to print np.transpose of q1 at q2, just to make sure they're orthogonal, and I'll run this. And let's see what we got. All right, now look. All right, I'm here. And you can see that this is basically 0. There's some numerical error, but this is basically 0. All right? So now I'm done with this. I can go and do this one again. Okay, notice that when you execute this code, then Python remembers what you've executed. So all the values of v and a are stored now. Okay, so I want to go here. Let's see how this one works. Let's see if we still get 0 when we do this. So I'm going to run this. Okay, and it looks like v is okay this time. Okay, all right. So the print v is okay. So we should be able to normalize this. Okay, so here I'm going to actually take this off here. So now let's do print Q3. So the takeaway is you should print your results and make sure everything is working correctly. So Q3 is like this. And let's do print np.transpose of Q1 at Q3. That's 1. And then we can do print np.transpose Q2 at Q3. Okay. Let's see what happens here. And you can see that these are basically both 0. Okay. All right, now you can go through the third time, and so you can finish by going through the third time. Okay. You're gonna do k equal 3. So I'll ask you to do that. Okay. And then I also will ask you to so please do the same thing. The entire process for a 3x3 matrix. For the matrix, and let me give you one. Let's get one that we know is not singular. Here I can do 1, 2, 6, or okay 1, 2, 6, just to make it irregular, and then we'll do 2, 3, 11, and then we'll do what we'll do minus 1, minus 1. And then I think 1 will be fine. Okay. So please do the entire process for this matrix also. You can do it step by step. If you want to code a loop, that's fine. But at least I want you to be able to do this kind of calculation systematically with Python. And you can see it's not that involved as long as you're systematic and keep your variables in order and keep checking with print statements to see where you are. Okay? So hopefully that's a little bit helpful.